Methods of forming materials from chemicals. Chemical substances can be used to create materials with exceptional properties such as high strength, conductivity, and durability, which are crucial for various applications such as electronics, medicine, and energy. In this article, we will explore some of the methods used to create materials with unique shapes and structures using chemical substances. Sol-gel synthesis. Sol-gel synthesis is a method to produce materials from a solution of metal salts or metal alkoxides, resulting in materials with exceptional properties such as high surface area and porosity. Sol-gel synthesis can be used to produce various materials such as ceramics, glasses, and composites, and is used in various applications such as catalysis and sensors. Electrochemical deposition. Electrochemical deposition is a method to produce materials by depositing metal ions onto a conductive substrate using an electric current, resulting in materials with exceptional properties such as high purity and uniformity. Electrochemical deposition can be used to produce various materials such as metals, semiconductors, and polymers, and is used in various applications such as microelectronics and energy storage. Chemical vapor deposition. Chemical vapor deposition is a method to produce materials by depositing vaporized precursors onto a substrate, resulting in materials with exceptional properties such as high purity and uniformity. Chemical vapor deposition can be used to produce various materials such as carbon nanotubes, graphene, and diamond, and is used in various applications such as electronics and biomedical devices. Atomic layer deposition. Atomic layer deposition is a method to produce materials by depositing thin films of atoms or molecules onto a substrate, resulting in materials with exceptional properties such as precise thickness and uniformity. Atomic layer deposition can be used to produce various materials such as semiconductors, dielectrics, and catalysts, and is used in various applications such as microelectronics and energy storage. Templated synthesis. Templated synthesis is a method to produce materials by using a template or mold to guide the shape and structure of the material, resulting in materials with exceptional properties such as high complexity and functionality. Templated synthesis can be used to produce various materials such as nanowires, nanotubes, and microspheres, and is used in various applications such as sensors and drug delivery. Colloidal synthesis. Colloidal synthesis is a method to produce materials by using colloidal particles as building blocks to form a material, resulting in materials with exceptional properties such as high stability and uniformity. Colloidal synthesis can be used to produce various materials such as quantum dots, nanoparticles, and nanocrystals, and is used in various applications such as electronics and biomedical imaging. Emulsion polymerization. Emulsion polymerization is a method to produce materials by using an emulsion of monomers and water to form a polymer, resulting in materials with exceptional properties such as high purity and stability. Emulsion polymerization can be used to produce various materials such as latex, adhesives, and coatings, and is used in various applications such as textiles and paper. Hydrothermal synthesis. Hydrothermal synthesis is a method to produce materials by using high pressure and high temperature water to form a material, resulting in materials with exceptional properties such as high purity and crystallinity. Hydrothermal synthesis can be used to produce various materials such as ceramics, zeolites, and metal organic frameworks, and is used in various applications such as catalysis and gas storage. Biomineralization. Biomineralization is a method to produce materials by using living organisms to form a material, resulting in materials with exceptional properties such as high complexity and biocompatibility. Biomineralization can be used to produce various materials such as bone, teeth, and shells, and is used in various applications such as tissue engineering and drug delivery. Freeze casting. Freeze casting is a method to produce materials by freezing a suspension of particles in a solvent, resulting in materials with exceptional properties such as high porosity and aligned structures. Freeze casting can be used to produce various materials such as ceramics, metals, and polymers, and is used in various applications such as tissue engineering and energy storage. Self-assembly. Self-assembly is a method to produce materials by using molecular interactions to form a material, resulting in materials with exceptional properties such as high complexity and functionality. Self-assembly can be used to produce various materials such as supramolecular assemblies, peptides, and DNA nanotechnology, and is used in various applications such as drug delivery and electronics. Microfluidics. Microfluidics is a method to produce materials by using microchannels to manipulate fluids and particles, resulting in materials with exceptional properties such as high precision and control. Microfluidics can be used to produce various materials such as microcapsules, microgols, and microspheres, and is used in various applications such as drug delivery and biosensors. Electrospinning. Electrospinning is a method to produce materials by using an electric field to draw fibers from a polymer solution, resulting in materials with exceptional properties such as high surface area and porosity. Electrospinning can be used to produce various materials such as nanofibers, membranes, and scaffolds, and is used in various applications such as tissue engineering and filtration. Plasma processing. Plasma processing is a method to produce materials by using plasma to modify the surface or structure of a material, resulting in materials with exceptional properties such as high reactivity and surface energy. Plasma processing can be used to produce various materials such as polymers, metals, and ceramics, and is used in various applications such as surface coatings and microelectronics. Biopolymer synthesis. Biopolymer synthesis is a method to produce materials by using biological organisms or enzymes to form a polymer, resulting in materials with exceptional properties such as biodegradability and biocompatibility. Biopolymer synthesis can be used to produce various materials such as bioplastics, biomaterials, and biofuels, and is used in various applications such as packaging and tissue engineering. Nanolithography. Nanolithography is a method to produce materials by using patterning techniques on a nanoscale level, resulting in materials with exceptional properties such as high resolution and precision. Nanolithography can be used to produce various materials such as nanowires, nanotubes, and nanodots, and is used in various applications such as microelectronics and nanomedicine. Atomic force microscopy. Atomic force microscopy is a method to produce materials by using a scanning probe to manipulate and characterize materials on a nanoscale level, resulting in materials with exceptional properties such as high resolution and sensitivity. Atomic force microscopy can be used to produce various materials such as nanosensors, nanorobots, and nanocomposites, and is used in various applications such as nanoelectronics and nanomedicine. Polymerization-induced self-assembly. Polymerization-induced self-assembly is a method to produce materials by initiating polymerization in a mixture of monomers and surfactants, resulting in materials with exceptional properties such as high uniformity and tunable properties. Polymerization-induced self-assembly can be used to produce various materials such as nanoparticles, micelles, and vesicles, and is used in various applications such as drug delivery and imaging. Supercritical fluid processing. Supercritical fluid processing is a method to produce materials by using a supercritical fluid to dissolve and precipitate a material, resulting in materials with exceptional properties such as high purity and high surface area. Supercritical fluid processing can be used to produce various materials such as aerogels, zeolites, and polymers, and is used in various applications such as catalysis and drug delivery. Applications of chemistry in the manufacture of conductors and insulators. Chemistry plays a vital role in the production of materials with unique electrical properties, such as conductors and insulators, which are critical for various applications in industries such as electronics, energy, and telecommunications. In this article, we will explore some of the applications of chemistry in the production of electrical materials. Conductive polymers. Conductive polymers are materials that have the ability to conduct electricity, and they are produced by doping a polymer with a conductive dopant. Conductive polymers can be used in various applications such as organic solar cells, flexible electronics, and sensors. Graphene. Graphene is a two-dimensional material composed of a single layer of carbon atoms arranged in a hexagonal lattice, and it has excellent electrical conductivity. Graphene can be produced by various methods such as chemical vapor deposition and exfoliation, and it can be used in various applications such as energy storage, sensors, and transistors. Carbon nanotubes. Carbon nanotubes are cylindrical structures composed of carbon atoms, and they have exceptional electrical conductivity due to their unique structure. Carbon nanotubes can be produced by various methods such as arc discharge and chemical vapor deposition, and they can be used in various applications such as nanoelectronics, energy storage, and sensors. Metal nanoparticles. Metal nanoparticles, such as gold and silver nanoparticles, have unique electrical properties due to their small size and high surface area. Metal nanoparticles can be produced by various methods such as chemical reduction and electrochemical deposition, and they can be used in various applications such as conductive inks, sensors, and catalysis. Dielectric materials. Dielectric materials are materials that do not conduct electricity but can store electrical energy. Dielectric materials can be produced by various methods such as sol-gel synthesis and chemical vapor deposition, and they can be used in various applications such as capacitors and insulators. Ceramic materials. Ceramic materials have unique electrical properties due to their high melting point and high thermal stability. Ceramic materials can be produced by various methods such as sol-gel synthesis and hydrothermal synthesis, and they can be used in various applications such as capacitors, insulators, and piezoelectric devices. Organic semiconductors. Organic semiconductors are materials that have intermediate electrical conductivity between conductors and insulators. Organic semiconductors can be produced by various methods such as solution processing and vacuum deposition, and they can be used in various applications such as organic solar cells, transistors, and sensors. Metal organic frameworks. Metal organic frameworks are materials composed of metal ions and organic ligands, and they have unique electrical properties due to their porous structure and high surface area. Metal organic frameworks can be produced by various methods such as solvothermal synthesis and microwave synthesis, and they can be used in various applications such as gas storage, catalysis, and sensors. Transparent conductive oxides. Transparent conductive oxides are materials that can conduct electricity while maintaining transparency to visible light. Transparent conductive oxides can be produced by various methods such as physical vapor, deposition, and sol-gel synthesis, and they can be used in various applications such as touchscreens, solar cells, and displays. Quantum dots. Quantum dots are nanocrystals that have unique electrical properties due to their size and composition. Quantum dots can be produced by various methods such as colloidal synthesis and molecular beam epitaxy, and they can be used in various applications such as displays, imaging, and solar cells. Electroceramics. Electroceramics are materials that have unique electrical properties due to their ionic conductivity and dielectric properties. Electroceramics can be produced by various methods such as solid-state sintering and sol-gel synthesis, and they can be used in various applications such as capacitors, sensors, and fuel cells. Polymer electrolytes. Polymer electrolytes are materials composed of polymers and salts, and they have unique electrical properties due to their ability to conduct ions. Polymer electrolytes can be produced by various methods such as solution casting and electrospinning, and they can be used in various applications such as batteries, fuel cells, and supercapacitors. Ferroelectric materials. Ferroelectric materials are materials that have unique electrical properties due to their ability to generate an electric field when subjected to an external electric field. Ferroelectric materials can be produced by various methods such as solid-state reaction and chemical vapor deposition, and they can be used in various applications such as memory devices, sensors, and actuators. Ionic liquids. Ionic liquids are salts that have unique electrical properties due to their ability to conduct ions and dissolve various materials. Ionic liquids can be produced by various methods such as electrochemical synthesis and metathesis reaction, and they can be used in various applications such as batteries, sensors, and separations. Conductive adhesives. Conductive adhesives are materials that have unique electrical properties due to their ability to conduct electricity and adhere to various substrates. Conductive adhesives can be produced by various methods such as mixing conductive particles with a polymer matrix, and they can be used in various applications such as flexible electronics, sensors, and touchscreens. Nanowires. Nanowires are cylindrical structures that have unique electrical properties due to their small size and high aspect ratio. Nanowires can be produced by various methods such as electrochemical deposition and vapor-liquid solid growth, and they can be used in various applications such as transistors, sensors, and solar cells. Thermoelectric materials. Thermoelectric materials are materials that have unique electrical properties due to their ability to convert heat into electricity. Thermoelectric materials can be produced by various methods such as solid-state sintering and mechanical alloying, and they can be used in various applications such as waste heat recovery and cooling devices. Photoconductors. Photoconductors are materials that have unique electrical properties due to their ability to generate an electric current when exposed to light. Photoconductors can be produced by various methods such as doping a semiconductor with impurities, and they can be used in various applications such as photodetectors, solar cells, and imaging devices. Ferromagnetic materials. Ferromagnetic materials are materials that have unique electrical properties due to their ability to generate a magnetic field. Ferromagnetic materials can be produced by various methods such as powder metallurgy and melt spinning, and they can be used in various applications such as magnetic storage, motors, and sensors. Superconducting materials. Superconducting materials are materials that have unique electrical properties due to their ability to conduct electricity without resistance at low temperatures. Superconducting materials can be produced by various methods such as solid-state reaction and chemical vapor deposition, and they can be used in various applications such as magnetic resonance imaging, power transmission, and quantum computing. Electroactive polymers. Electroactive polymers are materials that have unique electrical properties due to their ability to change their shape and size under the application of an electric field. Electroactive polymers can be produced by various methods such as polymerization and electrospinning, and they can be used in various applications such as actuators, artificial muscles, and sensors. Chalcogenide glasses. Chalcogenide glasses are materials that have unique electrical properties due to their ability to switch between conducting and insulating states when exposed to light. Chalcogenide glasses can be produced by various methods such as melt quenching and methods to separate organic and inorganic substances. Separation techniques play a crucial role in the isolation and purification of organic and inorganic compounds. These techniques are widely used in various industries such as pharmaceuticals, food, and chemicals, where the purity of the final product is critical. In this article, we will explore some of the common separation techniques used for organic and inorganic compounds. Organic compound separation methods. Distillation. Distillation is a technique used to separate liquids based on their boiling points. In this method, the mixture is heated, and the components with lower boiling points vaporize first and are condensed and collected separately. Distillation is commonly used to separate organic solvents or to purify liquids. Chromatography. Chromatography is a technique used to separate components in a mixture based on their affinity for a stationary phase and a mobile phase. The mixture is passed over a stationary phase, and the components with higher affinity for the stationary phase will move at a slower rate than the components with lower affinity. Chromatography is commonly used to separate and purify complex mixtures, such as proteins and nucleic acids. Extraction. Extraction is a technique used to separate a component from a mixture by selectively dissolving it in a specific solvent. The mixture is mixed with a solvent that will dissolve the desired component, and then the mixture is separated based on their solubility. Extraction is commonly used to isolate natural products, such as essential oils and plant extracts. Crystallization. Crystallization is a technique used to separate a component from a mixture based on its ability to form crystals. The mixture is dissolved in a solvent, and the solution is allowed to cool slowly, allowing the desired component to crystallize. Crystallization is commonly used to purify and isolate organic compounds, such as pharmaceuticals and chemicals. Inorganic compound separation methods. Filtration. Filtration is a technique used to separate solids from liquids or gases based on their particle size. The mixture is passed through a filter, which allows the smaller particles to pass through and retains the larger particles. Filtration is commonly used to separate solids from liquids, such as in wastewater treatment and mining. Precipitation. Precipitation is a technique used to separate a component from a mixture by adding a reagent that will cause the component to form a solid precipitate. The mixture is treated with a reagent that will cause the desired component to precipitate, and then the mixture is separated by filtration. Precipitation is commonly used to isolate and purify inorganic compounds, such as salts and metals. Electrolysis. Electrolysis is a technique used to separate a component from a mixture by passing an electric current through it. The mixture is placed in an electrolytic cell, and the component with higher electrical conductivity will be attracted to the electrode with the opposite charge. Electrolysis is commonly used to refine metals and to produce chlorine and sodium hydroxide. Ion exchange. Ion exchange is a technique used to separate ions from a solution based on their charge. The mixture is passed through a resin containing charge groups that will selectively bind to the desired ions, and then the mixture is separated by elution. Ion exchange is commonly used to purify and separate inorganic compounds, such as water softening and metal recovery. Evaporation. Evaporation is a technique used to separate a solvent from a solution based on their boiling points. The solution is heated, and the solvent vaporizes, leaving behind the desired component in a concentrated form. Evaporation is commonly used to isolate and purify inorganic compounds, such as salts and minerals. Gas chromatography. Gas chromatography is a technique used to separate and analyze small molecules based on their volatility and affinity for a stationary phase. In this method, the mixture is vaporized, and the individual components are separated based on their interaction with the stationary phase. Gas chromatography is commonly used in the chemical and pharmaceutical industries to analyze and purify organic compounds. Liquid-liquid extraction. Liquid-liquid extraction is a technique used to separate components in a mixture based on their solubility in two immiscible liquids. The mixture is mixed with a second liquid that selectively dissolves the desired component, and the two liquids are then separated based on their density. Liquid-liquid extraction is commonly used in the chemical and pharmaceutical industries to isolate and purify organic compounds. Centrifugation. Centrifugation is a technique used to separate components in a mixture based on their density and size. The mixture is placed in a centrifuge, which spins the mixture at high speeds, causing the denser components to sediment at the bottom of the tube. Centrifugation is commonly used in the biological and pharmaceutical industries to separate cells, proteins, and other biomolecules. Ion chromatography. Ion chromatography is a technique used to separate and analyze ionic species in a mixture based on their charge and affinity for a stationary phase. In this method, the mixture is passed through a column containing a resin with charged groups that selectively bind to the desired ions. Ion chromatography is commonly used in the chemical and environmental industries to analyze and purify inorganic compounds. Gel electrophoresis. Gel electrophoresis is a technique used to separate and analyze DNA, RNA, and proteins based on their size and charge. In this method, the mixture is loaded onto a gel matrix, and an electric field is applied, causing the molecules to migrate through the gel. The molecules are separated based on their size and charge, and can be visualized using stains or dyes. Gel electrophoresis is commonly used in the biological and medical industries to analyze and purify biomolecules. Magnetic separation. Magnetic separation is a technique used to separate magnetic materials from non-magnetic materials. In this method, the mixture is passed through a magnetic field, which selectively attracts the magnetic materials, and the non-magnetic materials are collected separately. Magnetic separation is commonly used in the mining and recycling industries to separate metals from non-metallic materials. Ultrafiltration. Ultrafiltration is a technique used to separate components in a mixture based on their size and molecular weight. In this method, the mixture is passed through a membrane with a specific pore size, which allows smaller molecules to pass through while retaining larger molecules. Ultrafiltration is commonly used in the food and beverage industries to purify and concentrate proteins and other biomolecules. Reverse osmosis. Reverse osmosis is a technique used to purify water and other liquids by separating dissolved salts and other impurities. In this method, the solution is passed through a semi-permeable membrane under high pressure, which allows water molecules to pass through while retaining the salts and impurities. Reverse osmosis is commonly used in the water treatment and desalination industries to produce clean drinking water and process water. Supercritical fluid extraction. Supercritical fluid extraction is a technique used to separate and purify organic compounds using a supercritical fluid, such as carbon dioxide. In this method, the mixture is exposed to a supercritical fluid, which selectively dissolves the desired component, and the two phases are separated. Supercritical fluid extraction is commonly used in the pharmaceutical and chemical industries to isolate and purify organic compounds. Adsorption. Adsorption is a technique used to separate components in a mixture based on their affinity for a solid phase. In this method, the mixture is passed over a solid phase, which selectively adsorbs the desired component, and the other components are collected separately. Methods of producing and processing plastic materials from chemicals. Plastics are ubiquitous in our daily lives, from the packaging of the food we eat to the electronic devices we use. Plastics are composed of polymers, which are long chains of repeating units made from various chemical monomers. The production of plastics involves several steps, including polymerization, compounding, and processing. Additionally, the handling and disposal of plastics present environmental challenges due to their non-biodegradable nature. In this article, we will explore the various methods used for the production and processing of plastic materials from chemical substances. Polymerization. Polymerization is the process of forming a polymer by combining monomers under specific conditions, such as heat, pressure, or radiation. There are two types of polymerization: addition polymerization and condensation polymerization. Addition polymerization. In addition polymerization, monomers are added together without the elimination of any byproducts, and the polymer grows through the addition of new monomers. This process is commonly used to produce polyethylene, polypropylene, and polystyrene. Condensation polymerization. In condensation polymerization, monomers react to form a polymer with the elimination of a small molecule, such as water or alcohol. This process is commonly used to produce nylon, polyester, and polyurethane. Compounding. Compounding is the process of adding various additives, fillers, or pigments to the polymer to modify its properties, such as strength, flexibility, and color. Additives can include stabilizers, antioxidants, and flame retardants, while fillers can include talc, glass fibers, and carbon black. Processing. After compounding, the polymer is processed into its final form. The most common processing methods include injection molding, blow molding, extrusion, and thermoforming. Injection molding. Injection molding is a process where molten plastic is injected into a mold cavity under high pressure. The plastic then solidifies and is ejected from the mold as a finished product. Injection molding is commonly used to make products such as toys, automotive parts, and medical devices. Blow molding. Blow molding is a process where a molten tube of plastic is inflated to the shape of a mold cavity. The plastic then solidifies and is ejected from the mold as a finished product. Blow molding is commonly used to make products such as bottles, containers, and tanks. Extrusion. Extrusion is a process where a molten plastic is forced through a die to create a continuous shape, such as a tube or sheet. The plastic then solidifies and is cut into the desired length. Extrusion is commonly used to make products such as pipes, films, and sheets. Thermoforming. Thermoforming is a process where a sheet of plastic is heated and then shaped over a mold using vacuum or pressure. The plastic then solidifies and is trimmed to the desired shape. Thermoforming is commonly used to make products such as trays, cups, and packaging. Handling and disposal. The handling and disposal of plastics present environmental challenges due to their non-biodegradable nature. Plastics can persist in the environment for hundreds of years, causing harm to wildlife and ecosystems. To mitigate these challenges, various strategies are being developed, such as recycling, biodegradation, and the use of sustainable materials. Recycling. Recycling is a process where plastic waste is processed and reused to create new products. The recycling process can involve mechanical, chemical, or biological methods, depending on the type of plastic and the desired end product. Recycling can help reduce the amount of plastic waste in landfills and the environment. Biodegradation. Biodegradation is a process where plastics are broken down into smaller components by microorganisms, such as bacteria and fungi. Biodegradation can occur naturally in the environment, or it can be facilitated through the use of biodegradable plastics. Biodegradable plastics are made from renewable resources and are designed to break down quickly in the environment. Sustainable materials. Sustainable materials are materials that are produced using environmentally friendly processes and are biodegradable or recyclable. Examples of sustainable materials include bioplastics, which are made from renewable resources, and natural fibers, such as bamboo and hemp. In recent years, there has been a growing concern about the environmental impact of plastic production and consumption. Plastic waste has become a major environmental issue, with millions of tons of plastic debris polluting our oceans, rivers, and landfills. To address this issue, there has been a push towards developing more sustainable materials and production methods. One approach is to develop bioplastics, which are made from renewable resources, such as corn starch, sugarcane, and potato starch. Bioplastics have the potential to reduce the environmental impact of plastic production and disposal, as they are biodegradable and compostable. However, there are challenges associated with the production of bioplastics, such as the use of land and resources needed to grow the crops used to produce them. Another approach is to develop new methods for recycling plastic waste. Currently, only a small fraction of plastic waste is recycled, with the majority ending up in landfills or the environment. To increase recycling rates, there have been efforts to develop new technologies for sorting and processing plastic waste, as well as to improve the infrastructure for collecting and recycling plastic waste. One promising technology for plastic recycling is chemical recycling, which involves breaking down plastic waste into its constituent molecules using chemical processes. This allows for the recovery of the original monomers, which can then be used to produce new plastic products. Chemical recycling has the potential to significantly increase plastic recycling rates and reduce the environmental impact of plastic waste. In addition to developing new materials and recycling methods, there is also a need to reduce the overall consumption of plastic. This can be achieved through a combination of measures, such as reducing unnecessary packaging, promoting reusable products, and encouraging changes in consumer behavior. Apart from the development of bioplastics and chemical recycling, there are various other approaches being explored to make plastic production and disposal more sustainable. One such approach is the use of nanotechnology to improve the properties of plastic materials. Nanotechnology involves manipulating materials at the nanoscale level, which can enhance the strength, durability, and biodegradability of plastics. Another approach is to develop materials that are designed to break down more quickly in the environment. For example, researchers are exploring the use of enzymes that can break down plastic waste into smaller molecules, which can then be biodegraded by microorganisms. This approach has the potential to significantly reduce the amount of plastic waste in the environment. In addition to developing new materials and processes, there is also a need for better waste management practices. Chemical reactions and production processes in the iron industry, including steel and iron production. The iron industry is a vital part of modern society, as it provides the raw materials for many essential products, including steel and iron. The production of these materials involves various chemical reactions and production processes that are critical to their quality and performance. In this article, we will explore the chemical reactions and production processes involved in the iron industry, including steel and iron production. Iron ore mining. The first stage in the production of steel and iron is mining iron ore. Iron ore is a rock that contains iron minerals, which are usually in the form of oxides, such as hematite or magnetite. The extraction of iron from these ores involves several chemical reactions, including reduction and oxidation. Iron ore processing. After mining, iron ore is processed to remove impurities and prepare it for use in the production of steel and iron. Processing involves crushing the ore to a fine powder, followed by separation using magnetic or gravity methods. The resulting concentrate is then further processed to remove impurities and increase its iron content. Blast furnace. The blast furnace is a critical component in the production of iron and steel. It is a large, vertical cylinder made of steel, lined with heat-resistant bricks. The furnace is charged with iron ore, coke, and limestone, and heated to high temperatures using a blast of hot air. The chemical reactions that occur in the blast furnace are complex and involve multiple steps. First, the coke reacts with the hot air to produce carbon monoxide gas, which reduces the iron oxide in the ore to metallic iron. This reaction is exothermic, producing heat that raises the temperature in the furnace. The limestone reacts with the impurities in the ore to form a slag, which is then removed from the furnace. Steel production. Steel production involves the refining of pig iron, which is produced in the blast furnace. The pig iron is heated in a furnace with oxygen or air to remove impurities and carbon content, resulting in steel. The refining process involves several chemical reactions, including oxidation, reduction, and decarburization. Casting and rolling. After steel production, the molten steel is cast into various shapes, including ingots, billets, and slabs. These shapes are then rolled into finished products, such as sheets, bars, and pipes. The rolling process involves heating the steel to high temperatures and then passing it through a series of rollers to achieve the desired shape and thickness. Iron production. The production of iron involves similar processes to steel production, but with different raw materials and reactions. Iron is typically produced in a blast furnace using iron ore, coke, and limestone. The resulting pig iron is then refined to remove impurities and produce iron of a desired purity. Casting and forging. After iron production, the molten iron is cast into various shapes, including pipes, fittings, and valves. These shapes can also be forged into finished products, such as bolts, nuts, and gears. Forging involves heating the iron to high temperatures and then shaping it using hammers or presses. Recycling. Recycling is an essential part of the iron industry, as it helps to conserve natural resources and reduce waste. Scrap metal can be melted down and used to produce new steel and iron products. Recycling involves similar processes to steel and iron production, but with different raw materials and reactions. In conclusion, the iron industry is a complex and multifaceted sector that involves various chemical reactions and production processes. The production of steel and iron involves mining, processing, blast furnace operations, steel production, casting, and rolling. The production of iron involves similar processes, but with different raw materials and reactions. Recycling is also an essential part of the industry, as it helps to conserve natural resources and reduce waste. Understanding the chemical reactions and production processes involved in the iron industry is crucial to producing high-quality steel and iron products that meet the demands of modern society. Galvanizing. Galvanizing is a process used to protect steel and iron products from corrosion. It involves coating the surface of the metal with a layer of zinc, which provides a sacrificial barrier that prevents the underlying steel or iron from rusting. The galvanizing process involves several chemical reactions, including the reaction between zinc and the iron or steel, and the formation of a zinc oxide or hydroxide layer on the surface of the metal. Electroplating. Electroplating is a process used to apply a thin layer of metal, such as chromium or nickel, onto the surface of another metal, such as steel or iron. Electroplating involves passing an electric current through a solution of metal ions, which causes the ions to adhere to the surface of the metal. The electroplating process involves several chemical reactions, including the reduction of metal ions to form a solid metal, and the oxidation of the metal being plated to form metal ions. Heat treatment. Heat treatment is a process used to improve the properties of steel and iron products, such as strength, hardness, and durability. Heat treatment involves heating the metal to high temperatures and then cooling it rapidly or slowly to achieve the desired properties. The heat treatment process involves several chemical reactions, including the formation of new phases and the rearrangement of atoms within the metal. Coating. Coating is a process used to enhance the performance of steel and iron products, such as by improving their resistance to wear, corrosion, and oxidation. Coating involves applying a layer of material, such as paint, powder, or enamel, onto the surface of the metal. The coating process involves several chemical reactions, including the curing of the coating material and the formation of bonds between the coating and the metal surface. In conclusion, the iron industry involves various chemical reactions and production processes, including mining, processing, blast furnace operations, steel and iron production, casting and forging, recycling, galvanizing, electroplating, heat treatment, and coating. Understanding these processes is critical to producing high-quality steel and iron products that meet the demands of modern society. By continually improving these processes and developing new ones, the iron industry can continue to play a vital role in the global economy and contribute to a sustainable future. Environmental impact. The iron industry, like many other industrial sectors, has a significant environmental impact. The production of steel and iron involves the extraction and processing of natural resources, such as iron ore and coal, which can have adverse effects on the environment. Additionally, the production processes themselves can generate air and water pollution, greenhouse gas emissions, and waste products. To address these environmental concerns, the iron industry has implemented various technologies and practices to reduce its environmental impact. These include using alternative fuels and energy sources, such as natural gas or renewable energy. Improving energy efficiency, reducing water consumption, and implementing waste management and recycling programs. Applications of catalysts in inorganic chemical reactions. Catalysts are substances that facilitate chemical reactions by lowering the activation energy required for the reaction to occur. They are widely used in the field of inorganic chemistry, where they play a critical role in various chemical processes. This article will explore the applications of catalysts in inorganic chemistry. Industrial applications of catalysts. Catalysts have been used for decades in the industrial production of various chemicals. One of the most significant applications of catalysts in inorganic chemistry is in the production of ammonia. Ammonia is a vital component in the production of fertilizers, and it is manufactured on a large scale using the Haber-Bosch process. The process involves the reaction of nitrogen gas and hydrogen gas over an iron-based catalyst at high temperatures and pressures. Another important application of catalysts in inorganic chemistry is in the production of sulfuric acid. Sulfuric acid is a widely used chemical in industry, and it is produced on a large scale using the contact process. In this process, sulfur dioxide gas is oxidized to sulfur trioxide gas over a vanadium oxide catalyst. The sulfur trioxide gas is then reacted with water to produce sulfuric acid. Catalysts are also used in the production of methanol and ethanol. Methanol is an important industrial chemical that is used as a feedstock in the production of formaldehyde, acetic acid, and methyl tert butyl ether (MIP). The production of methanol involves the reaction of carbon monoxide and hydrogen gas over a copper-based catalyst. Similarly, ethanol is produced via the catalytic hydration of ethylene. Environmental applications of catalysts. Catalysts are also used for environmental applications, particularly in the treatment of exhaust gases from vehicles and industrial processes. One of the most significant applications of catalysts in environmental chemistry is in the catalytic converter of automobiles. Catalytic converters convert harmful exhaust gases such as carbon monoxide, nitrogen oxides, and hydrocarbons into less harmful substances such as carbon dioxide, nitrogen, and water using a platinum-based catalyst. Catalysts are also used in the production of biodiesel. Biodiesel is a renewable fuel that is produced from vegetable oils and animal fats. The transesterification of these oils and fats into biodiesel requires the use of a catalyst, typically a base such as sodium hydroxide or potassium hydroxide. Inorganic chemistry applications of catalysts. Catalysts play a critical role in various inorganic chemistry applications such as oxidation, reduction, and hydrolysis reactions. One example of the application of catalysts in inorganic chemistry is in the oxidation of alcohols. The oxidation of primary alcohols to aldehydes and carboxylic acids requires the use of a catalyst, typically a metal such as chromium or manganese. Catalysts are also used in the reduction of metal ions to their corresponding metals. The reduction of iron 3 ions to iron 2 ions using a reducing agent such as zinc or tin requires the use of a catalyst such as hydrochloric acid or sulfuric acid. Hydrolysis reactions, which involve the breaking of chemical bonds by the addition of water, are also catalyzed. One example of a hydrolysis reaction is the hydrolysis of esters to their corresponding carboxylic acids and alcohols. This reaction is catalyzed by an acid such as sulfuric acid or hydrochloric acid. In recent years, catalysts have been increasingly used in emerging applications in inorganic chemistry. One such application is in the conversion of carbon dioxide to valuable chemicals. Carbon dioxide is a greenhouse gas and a major contributor to climate change. The use of catalysts to convert carbon dioxide into valuable chemicals such as methanol, formic acid, and dimethyl ether could potentially reduce carbon dioxide emissions and provide a sustainable source of chemicals. Catalysts are also being used in the development of new battery technologies. Lithium-ion batteries are widely used in electronics, but they are not suitable for large-scale energy storage due to their high cost and limited availability of lithium resources. Catalysts could potentially enable the development of new battery technologies such as flow batteries, which use cheap and abundant materials such as iron and copper. Inorganic catalysts are also being used in the development of new materials such as zeolites and metal organic frameworks. Zeolites are porous materials that are widely used as catalysts and adsorbents in industry. Metal organic frameworks are a new class of porous materials that have a wide range of applications such as gas storage, separations, and catalysis. Challenges in catalyst design. The design of efficient catalysts for specific chemical reactions is a complex and challenging task. Catalysts must be able to selectively promote the desired reaction while minimizing unwanted side reactions. They must also be stable and resistant to deactivation under the reaction conditions. One of the major challenges in catalyst design is the identification of the active site or sites on the catalyst surface. The active site is the location on the catalyst surface where the reactant molecules bind and undergo the desired reaction. The identification of the active site requires a thorough understanding of the catalyst structure and the reaction mechanism. Another challenge in catalyst design is the optimization of the catalyst properties such as size, shape, and composition. Catalyst properties can significantly affect the catalytic activity and selectivity. The use of advanced characterization techniques such as X-ray diffraction, transmission electron microscopy, and spectroscopy can provide valuable insights into the catalyst structure and properties. The development of new and more efficient catalysts for various chemical processes is an active area of research in inorganic chemistry. Future directions in catalyst research could focus on several areas such as developing catalysts for renewable energy conversion. There is an urgent need to develop sustainable energy sources to combat climate change. Catalysts could play a critical role in the conversion of renewable energy sources such as solar and wind energy into useful chemicals and fuels. Designing catalysts for selective and efficient chemical transformations, catalysts that can selectively promote the desired chemical reaction while minimizing unwanted side reactions could enable the development of new and more efficient chemical processes. Exploring new catalytic materials, there is a vast range of materials that could potentially act as catalysts. Research could focus on exploring new materials such as metal organic frameworks, carbon-based materials, and nanomaterials for catalytic applications. Understanding the mechanism of catalytic reactions. A thorough understanding of the mechanism of catalytic reactions is essential for the design of efficient catalysts. Technology of production and use of detergents and cleaning agents in daily life. Cleaning products are an essential part of our daily lives, helping us maintain clean and hygienic living spaces. From laundry detergents to dishwashing liquids, these products are designed to remove dirt, stains, and other unwanted substances from various surfaces. This article will explore the technology behind the production and use of cleaning products. Types of cleaning products. There are several types of cleaning products, each designed for a specific cleaning task. Some of the most common types of cleaning products include laundry detergents. These products are used to clean and remove stains from clothing and other textiles. They contain a combination of surfactants, enzymes, and other ingredients that work together to break down and remove dirt and stains. Dishwashing liquids. These products are used to clean dishes, utensils, and other kitchenware. They contain surfactants that help to break down grease and food residues. All-purpose cleaners. These products are designed to clean a variety of surfaces, including countertops, floors, and walls. They contain a combination of surfactants, solvents, and other ingredients that help to remove dirt and stains. Glass cleaners. These products are designed to clean and remove streaks from windows, mirrors, and other glass surfaces. They contain a combination of surfactants and solvents that help to dissolve and remove dirt and grime. Production of cleaning products. Cleaning products are typically produced in large manufacturing facilities using a variety of technologies. The production process typically involves several stages, including mixing, blending, and packaging. The first stage of the production process is mixing. The ingredients are weighed and measured according to the formulation of the product. The ingredients are then mixed together in large tanks using mixing equipment such as agitators or high-speed dispersers. Once the ingredients are mixed, they are blended to ensure uniformity of the product. The blended product is then transferred to the packaging area, where it is filled into bottles, containers, or other packaging materials. Quality control is an essential part of the production process. Testing is performed at various stages of the production process to ensure that the product meets the required specifications. This includes testing for appearance, viscosity, pH, and other properties. Use of cleaning products. Cleaning products are used in a variety of settings, including households, commercial establishments, and industrial facilities. The use of cleaning products is essential for maintaining clean and hygienic living and working environments. However, the use of cleaning products can also have adverse effects on human health and the environment. Some cleaning products contain toxic chemicals that can cause respiratory and skin irritations, and some can contribute to air and water pollution. To minimize these adverse effects, it is essential to use cleaning products responsibly. This includes following the instructions on the label, using the recommended amount of product, and disposing of the product properly. Emerging technologies in cleaning products. The cleaning product industry is constantly evolving, with new technologies and formulations being developed to improve the performance and sustainability of these products. Some of the emerging technologies in cleaning products include green chemistry. Green chemistry is an approach to chemical design that focuses on the development of products and processes that are environmentally friendly. Green cleaning products are formulated using renewable resources and biodegradable ingredients.